Study on water flushing times and water quality in southern Taylor Slough, Everglades National Park, Florida.
Good morning, everyone. Thank you for coming to see my presentation. So I'm going to start out with an outline. I'm going to go over an introduction, followed by my research objectives, followed by a study area with a site description, my methods, my conclusion, and my acknowledgements. So, water and yield time measurements have been used in a variety of studies from hydrological to geological to biological, to name a few. With the goal of quantifying the amount of time water remains inside a specified boundary, like say a watershed, the terms age, residence time, transit time, and flushing time have been used in the literature, usually with contradictory definitions. The terms age, residence time, and transit time focus more on the specific molecules that are entering and or are within a defined boundary, like say the watershed. Here I show you an image of say a specified boundary watershed, or watershed with specified boundaries, with the term age focusing on the amount of time that a molecule takes to reach say a location called point T, location T, from the entrance. While residence time focuses on the amount of time the molecule takes to exit the system from a specified location that's not necessarily the entrance. And then transit time does focus on the amount of time the molecule takes to exit the system all the way from the specified entry point. While flushing time is more of a system level measure, which focuses on the general exchange characteristics without really taking into consideration the spatial variability within the system and the importance. So age, residence time, and transit time focus more on the flow that's occurring within the system, while flushing time focuses more on the volume that's in the system and how it exits that system through the different output variables. So again, age and residence time are more locally focused, and they do have spatial variability within the system, while flushing time and transit time are more system-wide. So terms like age, residence time, and transit time are better for environments that are river-fed, and while an environment like the Everglades, which is a wetland and has dry periods, the term flushing time is more appropriate. So, ever since drainage first started in the 1880s in the Everglades, urbanization and water management practices have altered the natural flow of the Everglades. And this has resulted in a decrease of flow across the system. Today, the Everglades is half of its original size, with the most intact portion being in what is today called Everglades National Park. These effects have not only had hydrological changes to the system, but also topographical changes, which has resulted in an increase in groundwater and surface water interactions, groundwater seepage outside of the Everglades, water quality degradation, peat subsidence, and a decreasing number of tree islands. This general degradation has resulted in a lot of restoration projects to come into effect in the Everglades, with a goal of restoring natural flow to the Everglades to an almost pre-anthropogenic state, while also balancing flood control and urban water supply needs. Leading the way is the Comprehensive Everglades Restoration Plan, or CERP, established in the year 2000, with approximately 60 projects to be completed in the following 30 years. One of the main goals of CERP is to increase flow into Florida Bay via Taylor Slough. Projects to accomplish this goal include increasing natural flow into Taylor Slough via the headwaters by raising and lengthening Taylor Slough Bridge, which was finished in the year 2001. The S332D canal structure finished in 1999, the S332B finished in 2000, and the S332C finished in 2002, are basins that were created to produce what is called the hydraulic ridge, to prevent groundwater seepage outside of the Everglades National Park and into the lands east of the park, and to again increase flow into Taylor Slough. Now, C-111 Spreader Canal project is a continuation and a finalization of a 9-mile hydraulic ridge, again to increase flow into Taylor Slough, while also creating the Frog Pond detention area, and the S200 and S199 pump stations, which were completed in 2001. So previous work in Taylor Slough has lacked information on the water management practices and their effects on the water budget parameters, the water chemistry and nutrient data of Taylor Slough. The work presented here today will help in understanding Taylor Slough's hydrologic components in response to restoration efforts. Understanding the hydrological conditions of this wetland will also help in discerning other important variables like productivity, organic matter accumulation, and nutrient cycling and transport. Biogeochemical processes are affected by the amount of time water is made available for these processes to occur. So in other words, water flushing times are an important variable for the water quality of the system. So one way to assess the success of the restoration projects in this area are to observe long-term hydrological and geochemical changes as these restoration projects undergo completion. Understanding the long-term hydrological and geochemical changes will also help in discerning how variables like sea level rise and climate change may affect this area. So the purpose of this research was to investigate the effects of restoration on the water balance, flushing time, and water chemistry of Taylor Slough, with my research objectives being to determine water flushing times of Taylor Slough and how it has varied in the last decade from 2001 through 2011. To correlate the water flushing times with the surface water chemistry and analyze nutrients, and to identify the dominant sources of ions into Taylor Slough. My hypotheses were that with increasing surface water flow because of water management practices would result in a decrease in water flushing times of Taylor Slough, and that both major ion concentrations and nutrient values would have a positive correlation with these water flushing times, and that the groundwater input would be the major source of ions into Taylor Slough. So moving on to the study area of the Everglades. The Everglades extends from Lake Okeechobee, located in central Florida, all the way south to Florida Bay in the Gulf of Mexico. It is a freshwater coastal wetland with a subtropical climate of a wet summer season and a dry winter season. It is considered an oligotrophic ecosystem, with phosphorus being the limiting macronutrient. And the two main natural waterways are Shark Slough, which discharges out to the Gulf of Mexico, and Taylor Slough, which discharges out to Florida Bay. Taylor Slough itself extends approximately 20 to 30 kilometers from the northeast boundary of Everglades National Park all the way south to Florida Bay. The headwaters are located in the Rocky Glades, which is a geological outcrop part of the Atlantic Coastal Ridge. Taylor Slough transitions from a sawgrass-dominated freshwater emergent vegetation down to a transition zone, which has a mixture of freshwater vegetation and dwarf red mangroves, and then down to the coastal brackish area, which is dominated by dwarf red mangroves. This area where the dwarf red mangroves predominate is called the Everglades Mangrove Ecotone Region, or the EMER. Now, Taylor Slough is divided into northern and southern Taylor Slough by the main park road of Everglades National Park. Northern Taylor Slough includes the S332 detention basins and extends all the way down to Taylor Slough Bridge. Southern Taylor Slough, which is the majority of Taylor Slough, extends from Taylor Slough Bridge down to Florida Bay, has an area of approximately 446 square kilometers. The main park road to the north, the L31W to the east, Florida Bay to the south, and the Rocky Glades to the west compose the boundaries of southern Taylor Slough. And today, the surface water inflow is managed by the S332 deep pump station and the C111 canal. So the Florida Coastal Everglades Long-Term Ecological Research, the FCE-LTR, has sites at both Taylor Slough and Shark River Slough. 5 of those sites were used for this study. Each site has a portable sampler and a rain gauge. Now, two freshwater sites of TSPH1 and TSPH2 are located in the northern portion of Taylor Slough. And both of these sites dry out during the dry season, and both the surface water and groundwater are fresh at this site, at these two sites, with sawgrass being the major vegetation. Located at the northern end of the Everglades mangrove ecotone region is TSPH3, which also dries out during the dry season. Here the surface water is fresh, while the groundwater is brackish. And the dominant vegetation here is a mixture of sawgrass and the dwarf red mangroves. The two coastal sites of TSPH6 and TSPH7 are located in the Everglades mangrove ecotone region. Here both the groundwater and surface water tend to be brackish. And the dominant vegetation here are dwarf red mangroves. And there's also a weather tower located at TSPH7. So moving on to my methods of water, I calculate flushing times, my chemical analysis, and my flux of ions. So flushing times was calculated using the equation of volume over total output. And it was calculated on a monthly time scale from January 2001 through December 2011. It was also calculated on a daily, weekly, bi-weekly, and monthly time scale from January 1st, 2008 through July 31st, 2009, using data by Javier Zapata Rios. And then it was compared on a monthly time scale with the values obtained for this study. So looking at the numerator of flushing times volume, which is defined as the multiplication of water depth and area. To obtain water depth, I obtained surface water level data and subtracted that by the digital elevation model, or DEM. So the surface water level data I obtained from the Everglades Depth Estimation Network, or EDEN, which is a monitoring network of continuous water level data. And I used the 37 stations shown in this image. And aside from surface water level data, I also obtained precipitation and evapotranspiration data from these 37 stations. So to obtain the surface water level data, I used the first day of each month from January 2001 through January 2012 and created a 400 by 400 meter raster grid using spatial analyst grading on GIS. From January 2008 through July 2009, the same procedure was done on a daily basis. Now to create the DEM that I used, also on a 400 by 400 meter scale using GIS spatial analyst grading, I used data from the high accuracy elevation data, the HADs, which was data collected from 1995 through 2007 by the USGS, with an elevation point every 400 meters, and a vertical accuracy of plus or minus 15 centimeters. And the data was collected via truck, airboat, and helicopter. So once I obtained the water depth data, I multiplied that by the area of Taylor Slough, which was 446 square kilometers, and obtain my volume. So for the denominator of flushing times, total output, it was composed of evapotranspiration, surface water outflow, and groundwater recharge. To obtain the groundwater recharge variable, I used the water budget equation. For precipitation, I used again the 37 stations from EDEN and obtained data from 2002 through 2011. EDEN received the daily rainfall values from the South Florida Water Management District, and they obtained those values using the NextRad weather surveillance radar 88 Doppler. And these daily rainfall values were then summed up per month, and using GIS created Tyson polygons, which were then rasterized. For 2001, I used 10 stations from Everglades National Park, South Florida Water Management District, and NOAA, and using the same procedure created Tyson polygons, which were then rasterized. Now for surface water inflow data, I used the station of Taylor Slough Bridge, which was a compilation of 23 culverts and bridges that discharge into Taylor Slough. I also used discharge data from the S332D station, pump station, to compare the discharge data with the Taylor Slough Bridge data. For surface water outflow, I used the 3 coastal sites of McCormick Creek, Taylor River, and Mud Creek to obtain daily outflow data. And obviously this daily inflow and outflow data was then summed up per month for each variable. For evapotranspiration, again, the 37 Eden stations were used, and Eden received daily potential evapotranspiration data from the USGS, which they then extrapolated by location for stations. The evapotranspiration data was calculated using the Priestley-Taylor method, with radiation values obtained using NOAA's GOES East satellite. These daily ET values were then summed up per month, and using GIS spatial analyst kriging again, I created an ET layer. So for the change in storage, I used the difference of monthly volume obtained from the water depth raster layers. So for the current month's change in storage, I used the preceding month's water depth raster and subtracted that by the current month's to get that month's change in storage. And for R, which was recharge, this signified either groundwater discharge or recharge into Taylor Slough. A positive R meant that groundwater was discharging into Taylor Slough, while a negative R signified groundwater was being recharged by Taylor Slough. So the relationship between precipitation, surface water inflow, surface water outflow, and change in storage would help identify between climate and restoration efforts. An increase in the ratios of surface water inflow and precipitation, surface water outflow and precipitation, and the change in storage and precipitation would signify to an increase of flows due to restoration efforts, while a decrease in these ratios would signify a precipitation effect, as opposed to restoration efforts. So water samples were analyzed for the anions of chloride and sulfate and the cations of sodium, potassium, magnesium, and calcium. Groundwater samples ranged from November 2011 through July 2012, while the surface water samples ranged from August 2008 through July 2012. The samples were a combination of field campaigns and the stations from the FCE LTER. From 2001 through 2008, data was collected from historical databases and literature references. Now, the nutrient analysis focused on total nitrogen and total phosphorus, which the data was obtained from signature datasets collected from the FCE LTER website. And the water chemistry was then compared, analyzed, and correlated with water flushing times. So field campaigns were performed to go to Taylor Slough Bridge, TSPH 3, TSPH 6, and TSPH 7. The groundwater wells at Taylor Slough Bridge and TSPH 3 were purged 3 well volumes for 5 minutes using a high velocity gas pump. Then a peristaltic pump was used to collect both groundwater and surface water samples. During these field campaigns, conductivity, salinity, temperature, and pH were also recorded. Now, samples from the FCE LTER sites were collected from an ISCO sampler, with each sample being a 3-day composite of 250 milliliter surface water sample collected every 18 hours. A grab sample was also collected during these outings, which were done on a monthly time scale to collect the samples from the ISCO sampler. Now, the analysis of stable isotopes of oxygen and hydrogen were performed in the freshwater portion of Taylor Slough. And both groundwater and surface water samples were collected from Taylor Slough Bridge, TSPH 3, the monthly FCE LTER graph samples, and the FIU rain collector located on this campus on the AHS Center 2 building. And this analysis was used to support the dominant inputs of water into the freshwater portion of Taylor Slough. So the major sources of ions into Taylor Slough have included surface water inflow, precipitation, and groundwater inputs. The proportions of the inputs were used from physical and chemical data. The physical data came from the water budget equation, while the chemical data for chloride and calcium ions came from TSPH 2 to represent surface water inflow, the site FL11 from the NADP National Trends Network to represent precipitation, and the TSPH3 and Taylor Slough Bridge to represent groundwater, the groundwater input. So the yearly sum of the physical input was then multiplied by the yearly average of the chemical input for the years 2009 and 2011. So moving on to my results first, we're starting out with water flushing times. When water flushing times were calculated on a daily time scale, there was a lot of variability, but there was also the seasonal variability. And values ranged from 1 through 762 days. When the flushing times were calculated on a weekly and bi-weekly and monthly time scale, it was observed that variability decreased with the longer time scale, but the important signatures and seasonal variability was still captured. When the flushing times calculated using Zapata, Rios, and Price's data was compared to the flushing times calculated for this study, they had a correlation of 85%. The major difference between the two data sets was how each study obtained their evapotranspiration data. Zapata, Rios, and Price used the Penman-Monteith equation and used the weather tower located in TSPH7, while this study used the potential evapotranspiration data obtained from the Eden stations. So looking at the long term for the 10-year study period of flushing times, we again see the seasonal variability with longer flushing times observed during the later months and decreasing down through May. Values range from 3 to 78 days for this study. When looking at the monthly average of flushing times, again we see this seasonal variability, with the longest average flushing time occurring in the month of December for 54 days, while the shortest occurring in May of 11 days. When we look at the numerator of flushing times volume in the purple bar graph, the purple bars, and flushing time in the blue diamonds, we see that volume has a very similar trend as flushing times, increasing during the later months and decreasing through May. The highest observed volume was in the month of September 2005, which was the month following the passing of Hurricane Katrina through South Florida. And this was also a very active hurricane season. But when we look at the yearly total volumes, it was 2003 which had the highest yearly total, followed by 2010. When we include precipitation yearly totals to the graph, it was observed that when precipitation had higher yearly totals, volume also had higher yearly totals, and when precipitation was lower, volume was low too. When we see the monthly average, including volume, which is in the purple triangles on the graph, again we see the similar trend, with the lowest monthly average of volume being in May and the highest in October. When we look at the denominator of flushing times, the total output, which is again the combination of surface water outflow, evapotranspiration, and groundwater recharge. Evapotranspiration was the variable that had the highest input, composing approximately 76% of total output. Here represented in the red bars, it was observed that when we had higher evapotranspiration values, flushing times tended to be shorter. And when flushing times were longer, evapotranspiration was shorter. This is better observed in the monthly average graph, when we saw that the highest monthly average for evapotranspiration in May coincided with the shortest monthly average of flushing time. And when we had the lowest monthly average of evapotranspiration in December, it coincided with the longest monthly average of flushing time. So when we look at the relationship of evapotranspiration with flushing time, this had an R-squared of about 0.4. When we look at the relationship of volume with flushing time, this had an R-squared of 0.5. So evapotranspiration does have the largest influence for total output, but volume has the higher influence in the flushing times. So flushing times values range from 3 to 78 days, with values of 35 days or longer composing approximately 57% of the values. Of the denominator of total output, evapotranspiration had the major contribution, composing approximately 76% of the values. And it was observed that when we had shorter flushing times in May, evapotranspiration was at its highest. And when we had the longer flushing times in December, evapotranspiration was at its lowest. So we put the three variables on this monthly average. It was observed that when volume was greater than evapotranspiration values, we observed longer flushing times of 40 to 50 days. While when volume was less than ET, we saw shorter flushing times of less than 40 days. So in conclusion, surface water volume does have the highest influence on flushing times. So with increasing or decreasing volume into southern Taylor Slough, we should also see an increase or decrease in flushing time. So moving on to the precipitation ratio, starting with the surface water input and precipitation ratio, we did see a seasonal variability, with April and May having ratios of almost 0 or 0 due to the fact that there's very little to no inflow from Taylor Slough Bridge into Taylor Slough. And then we saw an increase in the ratio with more inflow coming in from Taylor Slough Bridge and precipitation decreasing. And there was a high monthly average in December. So looking at the cumulative of Taylor Slough Bridge inflow and cumulative rainfall at Taylor Slough Bridge in the lighter color and Royal Palm Ranger Station in the darker color, you can see that the ratio increases during the later months of the year and decreases during the earlier months of the year. And there was also an observed decrease in the ratio, in the slope between October 2005 and September 2008. When we look at the long term for the 10 years of surface water inflow in orange and rainfall at Taylor Slough Bridge in purple, and we focus in that time period of 2005 through 2008, we do see a decrease in both rainfall and surface water inflows. When we look at the surface water outflow and precipitation ratio, and then we see a bit of a seasonal variability, with a peak in November and a low in June. The relationship of surface water outflow and precipitation had an R² of about 0.2. When we look at the change in storage and precipitation ratio, it was observed that there was a bit of the ratio kind of stayed the same between May and September. And it peaked in January and a low in September. And the relationship between change in storage and precipitation had an R² of about 0.4. So from the three ratios that were observed, surface water inflow and precipitation that ratio had the highest insight into water management effects, with an observed decrease in slope during the dry season and an increase in slope during the wet season. And then again, seeing that decrease in slope during October 2005 and September 2008 due to decreased flows into through Taylor Slough Bridge and decreased rainfall at Taylor Slough. So Renshaw and Coden did see a noticeable increase in slope during a longer time scale from 1960 through 2010, when they were looking at restoration projects with the goal of increasing flow into Taylor Slough. When we looked at the relationship between the flow at Taylor Slough Bridge and the flow discharge at S332, this had a relationship of an R² of 0.6. When observing the Taylor Slough Bridge flow and comparing that to the rainfall at Taylor Slough Bridge, this had an R-squared of about 0.2. So it shows the high influence of the discharge at S332 to the inflows into southern Taylor Slough. And although positive effects of water management and restoration efforts have been observed at Taylor Slough, the environment is still precipitation driven. And if there is low precipitation, there will be low inflows from S332 and into Taylor Slough Bridge and eventually down to southern Taylor Slough. So moving on to the chemical analysis. In this graph and the following graphs, flushing times will be on the left y-axis and represented in the gray diamonds, with the chemical analysis on the right y-axis. And here I'm showing you calcium, with TSPH1 in green, TSPH2 in red, and TSPH3 in blue. What was observed at these three freshwater sites was that iron concentrations decreased as we moved further south into the system. Except during the months of February through June, where concentrations at TSPH3 for sodium, potassium, and chloride increased over the other two sites. There was also an observed lack of datum in TSPH1 between February and April due to this site drying down and not being able to collect surface water samples. Now for total nitrogen at these freshwater sites, the reverse gradient was observed with increasing concentrations as we moved further south into the system. Except during October and December, where again concentrations decreased as we moved further south into the system. Now these sites are full of the nitrogen fixing calcareous periphyton, which is believed to be the main source of nitrogen at these sites. Now for total phosphorus, we observed peaks at TSPH1 in January and October, while at TSPH2 they were observed and 3 they were observed in March. So this is believed to be an evaporation effect, and the biotic and abiotic processes that occurred during these March dry downs, showing these peaks and then the decrease in the concentration. Now for the coastal sites of TSPH6 shown in orange and TSPH7 in purple, the TSPH7 concentrations were always higher than at TSPH6, and both sites showed a seasonal variability, with increasing concentrations during shorter flushing times and decreasing concentrations during longer flushing times. When we include the variable of R, which is groundwater recharge or discharge, with the coastal sites, it was observed that when R was positive, which means groundwater is discharging, ion concentrations increased at these two coastal sites. And when R was negative, which means groundwater was being recharged, concentrations decreased. Now TSPH6 had an R-squared relationship with this R variable of about 0.5, while TSPH7 had an R-squared relationship with R of 0.4. Now for total nitrogen at the two coastal sites, concentrations remain relatively, they both had the similar values and trends, and they remain relatively constant throughout the months, with a slight peak in March. Now for total phosphorus at TSPH6, there was an increase between March and June, which was not observed at TSPH7, which remained relatively constant throughout the months and seasons. Now when we look at the stable isotopes of oxygen and hydrogen at the freshwater sites, all the values remained below the meteoric water line. The values at Taylor Slough Bridge for both surface water and groundwater remained relatively constant from the from the data collected in 1999 and the data collected now in 2011-12. But the groundwater at TSPH3 did show a positive increase from negative values in 1999 to more positive in 2009 and 2012. Now in 1999, Price and Stewart did identify the source of this groundwater to be from the rocky glades. But the positive isotopic values observed today signify to another source, and it could potentially be a marine input, but just looking at the isotope data is not possible to decipher. So when we look at the concentrations of chloride and calcium at these same freshwater sites, groundwater ions at TSPH3 from 1999 resembled the other freshwater sites. But when we look at the values of today, they're much higher, which signal to a seawater intrusion occurring at the groundwater at TSPH3, with these ion concentrations resembling concentrations at the coastal sites. Now when we look at the same ion concentrations in the groundwater at TSPH3 and compare that to the surface water, again we see that very large difference in the concentrations, which signal to a lack of surface water and groundwater interactions occurring at TSPH3. So from the three freshwater sites, TSPH3 proved to have the highest relationship with flushing times, with the ion concentrations of sodium, potassium, and chloride increasing with shorter flushing times and decreasing with longer flushing times. This relationship is probably observed due to an evaporation effect, and also because the local rainfall has been identified to have low but detectable sodium and chloride concentrations due to sea spray. We also saw a decrease in concentrations from TSPH1 down to TSPH3. And this signals to the decreased influence of surface water inflow from the S332 pump stations and an increased influence of precipitation down at TSPH3. Total nitrogen at TSPH3 also showed a similar trend to sodium, potassium, and chloride. And this is probably due to an evaporation effect and the cyanobacteria and the calcareous periphyton mats located at TSPH3 providing most of the nitrogen at the site. Now, two coastal sites of 6 and 7 were inversely related to flushing times, increasing with shorter flushing times and decreasing with longer flushing times. This is probably due to, again, high evapotranspiration and low precipitation, increasing these concentrations during the shorter flushing times. But it could also be due to groundwater discharging at these coastal sites. Previous work at these two coastal sites did show a relationship between ion concentrations and the groundwater recharge discharge. So with shorter flushing times, there is usually an increase in ion concentrations and groundwater discharge. While with longer flushing times, there is a decrease in ion concentrations and groundwater recharge. So with longer flushing times, it is believed that ion concentrations at the coastal sites will decrease. Now moving on to the flux of ions. Groundwater at TSPH3 showed to have the highest flux of ions, with the values an order of magnitude or more higher than the other ion fluxes, with groundwater at Taylor Slough Bridge showing the second largest value, but again nowhere near close to the ones at TSPH3 groundwater. And precipitation had the lowest ion fluxes. But ionic data shows no evidence of a surface water groundwater interactions going on at TSPH3. So right now, the flux of ions at TSPH3 groundwater has the potential of having the highest flux of ions into Taylor Slough. So when we look at the concentrations of chloride and compare that with stable isotope of oxygen, it is observed. We see an observed increase in values of both oxygen and chloride as we move further south into the system and through time, with a threshold of about 1.5 per mil for oxygen. Yeah, there we see that. So this signals to an evaporation line and leads me to the conclusion that rainfall is the major source of ions into the freshwater portion of Taylor Slough, with an increase in values downstream and through time at the freshwater sites. And the increased values of chloride at the groundwater sites definitely signal to seawater intrusion occurring at TSPH3. So in conclusion, the relationship of volume and evapotranspiration showed that when when volume was greater than evapotranspiration, we observed longer flushing times of 40 days or more. And when evapotranspiration was greater than volume, we observed shorter flushing times of less than 40 days. So with increasing surface water volume as a result of changing water management practices, will result in longer flushing times in southern Taylor Slough. The surface water chemistry at the coastal sites and TSPH3 showed a negative correlation with flushing times, increasing with shorter flushing times and decreasing with longer flushing times. And total nitrogen at TSPH3, which is located at the northern end of the Everglades mangrove ecotone region, also had a negative correlation with flushing times. So with longer flushing times, it will result in a decrease in iron concentrations in the Everglades mangrove ecotone region of southern Taylor Slough. And finally, the major source of ions to the freshwater portion of Taylor Slough is believed to be precipitation, with an increase in the stable isotope of oxygen, ions, and nutrients showing an evaporation effect during the dry season. And I would like to thank the FCELTR, the National Science Foundation, everyone at the Hydrogeology Lab, and my advisory committee and family and friends for helping me with this study. And this completes my presentation.
Okay, so now we'll entertain questions from the audience. Any audience members have questions?
I have two questions. With the ET map that you got from NextRad, correct? You got the ETs from that? When you did your ET calculations?
That was precipitation. They got it from NextRad.
So where's the ET data that you did the water balance with?
Mm-hmm.
Did you compare those to the weather stations to see, or you just used that as PET?
Yeah, I just used it.
And then the second question is, with water entering the Taylor Slough from the pump station, I mean, that's sitting in a canal, right? And that's coming over from it. Is that how the pump works? It's pumping from the canal.
Oh, I think,
into the
yeah, I
system?
think it comes from that.
So that's going to have a higher evaporation from the standing water there that's pumped in. Do you think that's going to drown out any precipitation signal that you get over, essentially over the basement?
I don't think I understand. So
water coming into the slough is pumped from that station that has standing evaporated water.
Right.
Will that dilute any precipitation signal that you have over the entire basin, in the sense of you might be overestimating or underestimating certain things related to water management? Does that make any sense?
Not really sure it does make sense.
In terms of isotopes?
Yeah.
No, she showed very clearly that the rainfall is the dominant input into southern Taylor Slough. So rainfall is going to dilute out whatever small input you're having in SC32.
Okay, I guess I'm just
It's not
switching
going to be
between the two water
It's not going to be
basins.
the other way around. The rainfall's always going to dilute out whatever SC32
Brings into it.
So basically you have like less input from S332 and the rainfall is less. Also.
Yes.
I have a couple of questions. There's a lot of information. Excellent work.
Oh, thank you.
And I went to read your thesis, and then I'll be able to see a few things were just too much. Were one. But there are a few things that you mentioned to me. So, for example, right at the end, that longer flushing times will result on the